Recall that last time we introduced a logarithm, and in particular the logarithm is the inverse of the exponential function. For example, if we look at the log base b of x, then this is going to be the number that we need to raise b to in order to get x back. Right? So if we let this thing equal y, then this means that b to the y is equal to x. So we can see that these things really do convey exactly the same information. But in one case, we're inputting x and getting y out, and in the other, we're inputting y and getting out x. So the logarithm is the inverse of the exponential. We also had some properties not related to the fact that these are inverses of each other. For example, log base b of 1 is going to be 0. That's for any base b. And the reason for that is because any number to the 0 power is equal to 1. Another one was log base b of b is equal to 1. And the reason for that is b to the first power is b. The idea for today is to introduce a few more properties, namely the product property, the quotient property, and the power property. And this will allow us to do a couple of different things. First of all, we can take the logarithm of sort of a complicated expression, maybe, and expand it out into simpler things. Maybe they're easier to algebraically manipulate or evaluate or estimate with a calculator, I should say. And then we can do the opposite thing. We can take a whole bunch of different logarithms, as long as they have the same base, and combine them all together into one logarithm. And then last time I talked briefly about how when we actually estimate these logarithms, we're pretty much only going to use the base 10 log, which we wrote as log with no base present. It's just implied that it's base 10. Or we're going to use the natural log, which is the log of base e, where we just write ln x. And you may be wondering, how are we going to approximate other logarithms, right? So we're going to have something called the change of base formula that allows us to change the base of a logarithm into any base that we want. And that's how we're going to actually approximate logarithms, using just the base 10 or the base e. So to summarize the properties that we talked about last time in 4.3 and 4.3, we have these two, which I just wrote up on the board. Log base b of 1 is 0, log base b of b is 1. We also had these two down here, and these ones just arise because the logarithm and exponential are inverses of each other. So we're going to have some new ones for today. Okay, so here are our brand new properties, as of today properties. This one is called the product property. Product property. And that's because it's what we do with a product inside the logarithm. So the logarithm of a product of things. Logarithm base b of x times y is log base b of x plus log base b of y. This seems rather strange, right, that we can take the product inside here and we're going to split it up into two logarithms and we're going to add those things up. Similarly, we're going to have a quotient property. Quotient property. Okay, and this is what we do with a quotient inside the logarithm. Log base b of x divided by y is going to be log base b of x minus log base b of y. It's a very similar rule, but if we're dividing, we're just going to split up into two logarithms and then subtract. Finally, we have this one called the power property. Power property. And if we have x raised to a power inside the logarithm, we're going to be able to bring that power down out of the logarithm out front as a coefficient. That looks like log base b of x to the p is equal to p times log base b of x. So these are the three properties that we're going to work with. Okay, let's look at some basic examples for these properties. So how do we write the log base 3 of 2x? Well, that one's going to be the product property, which tells us that's going to be base 3 log of 2 plus the base 3 log of x. Why might this make things easier? Well, log base 3 of 2, that's something that you could estimate with your calculator. So this thing is a number, where this thing is still a variable that depends on x in some way. So maybe that makes your life easier in some certain situation. This one, also a product property. So that's going to be the log base 4 of 16 plus base 4 log of 4. What's the base 4 log of 4? Well, we're calling our property that the base b log of b is equal to 1. This is going to be 1. Reason for that, again, is that 1 is the exact power we need to raise 4 to get 4. So we could rewrite this as log base 4 of 16 plus 1. So it's easy to see in this case how things got a little bit simpler or easier. This one, that's the natural log of x divided by y. That's going to be ln x minus ln y, and that's all we can do. Here we have the log base b of r to the 4th. So we're going to use the power property, which tells us we can pull the 4 out front. And we're going to get 4 times the log base b of r. And again, an expression on this one is the best we can do. Finally, we're going to revisit this problem from before, where we had the base 4 log of 16 times 4. So we already had, from up here, we had that this is the base 4 log of 16 plus 1. But we can take it a little bit further because 16 is equal to 4 squared. So we can write this as log base 4 of 4 squared plus 1. Okay, so now we're going to use the power rule on this, and that's going to be 2 times the base 4 log of 4 plus 1. And of course, the base 4 log of 4, as we showed before, is just equal to 1. So this is 2 times 1 plus 1, or in other words, 3. So in this particular case, it may not have looked like we could have done this in our head at all without using a calculator, but in fact, this one, because it splits up using 2 separate rules, we can solve it exactly, and the answer is 3. Okay, here are a few more examples. We're going to expand these single logarithms out using our new properties. So this one, again, we're going to use the product rule on this logarithm here because we have the product of 4 and p. And this is log of 4 plus log of p, just going straight down the definition of that property. Notice here that we're not showing a base, so that means implicitly this is base 10. For this one, do we have a property that deals with this, the 5th root of 6? Well, we have to recall that that 6 with the root symbol and this 5 right here, the 5th root, that's equal to 6 to the 1/5. So that's a fractional power. But it's a power like any other, and we can use the power rule on this. So this is going to be, I guess I'll write this in as a log of 6 to the 1/5, which we can use the power property on. Pull the 1/5 out front. 1/5 natural log of 6. This one right here, we're just given a base of c, and we're going to use the quotient property on this. It's going to be log base c of 14 minus log base c of 23. Okay, here's a slightly longer example. We might have to use a bunch of different properties in different order to be able to get this simplified. So first I'm going to get rid of this division right here by using the quotient property. This is going to be the base 3 log of x squared y to the 5th, and then minus base 3 log of m cubed times n squared. Okay, so just using the quotient property on x squared y to the 5th and m cubed into the, that should be into the fourth, I should say. There we go. It doesn't look like a 9. There we go, into the fourth. Next thing we can do is split up each of these products using the products property, so we can have actually 4 terms now. This is going to be equal to base 3 log of x squared plus base 3 log of y to the 5th. Then we're going to have minus base 3 log of m cubed, and then minus base 3 log of n to the 4th. Now, notice that the second term right here by itself would give us base 3 log of m cubed plus base 3 log of n squared, into the fourth. But since I'm subtracting off the entire term, that's going to be minus minus. Okay, now notice that each of these inputs for the log functions has a power, so we can use the power rule on each of them. If we do that, we're going to get 2 base 3 log of x plus 5 base 3 log of y minus 3 base 3 log of m minus 4 base 3 log of n. So we've taken this sort of compact, complicated logarithm and written it as this sum of much simpler logs to deal with using our properties. Here's another longer example. This time, what's on the outside of this expression, the very first thing that we're going to have to deal with, is the square root. So recall that the square root of x can be written as a fractional power, x to the 1/2. So what we have up here is this entire expression to the 1/2. So let's write it that way first. X cubed, y to the 4th, over z to the 6th, all of that to the 1/2. And so we can invoke the power property first and write that this is 1/2 times the natural log of x cubed, y to the 4th, over z to the 6th. We still have this 1/2 to deal with. Now we're able to use the quotient property to get rid of this z to the 6th in the denominator here. So let's go ahead and do that. That's going to be log of x cubed, y to the 4th, and then minus log of z to the 6th. Next, we can split up this product here using the product property. So that'll be log of x cubed plus log of y to the 4th. And then we still have minus log of z to the 6th. And then the last thing we can do is use the power property on each of these individual logarithms. So that's going to look like 1/2 1/2 times 3 log of x plus 4 log of y minus 6 log of z. And then finally, we can multiply through by 1/2 to each term. It's 3/2 log x plus 4/2, or 4/2 is 2. So 2 log y. And then minus 6/2. 6/2 is 3. So minus 3 log of z. And here's one more example of expanding using the properties. This one looks a little bit like the last one where we have the square root, but it's a little different in a couple of ways. So we'll start out in the same way by writing what's in the square root as instead the expression to a fractional power. So that's x squared plus 6 over e cubed to the 1/2. And then once again, we'll start by using the power property on this logarithm. So this is going to be 1/2 times the log of x squared plus 6 over e cubed. And then we'll use the quotient property again. Okay, so I've just taken log of x squared plus 6 and then subtracted off log of e cubed. Okay, now we can use the power property on the second logarithm. So what happens when we do that? We get 1/2 log of x squared plus 6, and then minus 3 times the natural log of e. But what's the natural log of e? Well, the natural log is just the log base e. And by one of those properties that we talked about last time, this is equal to 1, because 1 is the power that you have to raise e to get e back. So the natural log of e is just equal to 1, and so we can plug in 1 right here. We're going to get 1/2 as the log of x squared plus 6 minus 3 times 1. 3 times 1 is just 3. And then be careful at this step. You might be tempted to try to split this up by saying that this is like maybe the log of x squared plus the log of 6 or something like that, and this is not true. Right? So we actually don't have a rule that allows us to split up logarithms of sums. Right? The way it goes is product goes into a sum of logarithms, but we don't have anything to do, we don't have any way of dealing with this thing right here. So that logarithm is already in its simplest form, and we get 1/2 as the logarithm of x squared plus 6 minus 3/2. And we're done. So what about the opposite problem? How can we express multiple logarithms as a single logarithm? Well, we're just going to use these rules backwards. So in this case, we see log base a 14 plus base a log of 3. This looks like we've done the product property on something. So we can write this as the base 3 log of 14 times 3. And look back and check. Yes, of course, if we split this thing up using the product property, we're going to get log of 14 plus log of 3. And 14 times 3 is, what's that? It's going to be 30 plus 12, so 42. So for the second one, what jumps out immediately to me is that we have this subtraction right here that makes it look like we've done the quotient property. So let's write this as 2 log of x plus 3 log of y over z. And then for sure, yes, if we had log of y over z, we would split that up using the quotient rule by subtracting those individual logs. So far, so good. Now we're going to have, well, we can use the opposite of the power property to put these coefficients inside as powers. So we're going to have log of x squared and then plus log of y over x, that quantity cubed. Y over x cubed is going to equal y cubed over x cubed. So when we raise a fraction to a power, it's the same as if we raise numerator and denominator to that power. So we can rewrite this as log of x squared plus log of y cubed over z cubed. And this should be a z. That should be a z. There we go. Much better. Okay, so finally we have, this is the, we're adding two logarithms with different inputs, but the bases are the same. So we can use the product rule here, product property. So that's going to be the logarithm, and we're going to multiply these things together. So it's going to be x squared times y cubed over z cubed. And we're done. We have taken multiple logarithms with the same base and written it as one logarithm. Do notice that this only works if the bases are the same. Right, so in this case we had the base e, first case we had base a, but doing this trick only works, to combine logarithms together only works if you have the same base. Okay, here's another example that's just a little bit more challenging. So the first thing we're going to want to do is get rid of this difference right here by using the quotient property. So let's go ahead and do that. That's going to be logarithm of x squared minus 9 over x plus 3. And then we still have log of x plus y from here. Okay, so you may be noticing that if we factor x squared minus 9, we might get an x plus 3. And of course, this is the case. X squared minus 9 is a difference of squares. So it's going to factor as x plus 3 and x minus 3. And you can check this if you like. There's x squared minus 3x plus 3x, and the minus 3x and plus 3x will cancel, and then we get plus 3 minus 3, which of course is minus 9. So this means that x squared minus 9 over x plus 3 can be written as x minus 3 times x plus 3 over x plus 3. And this means that we can cancel the x plus 3's. Now you may be thinking, what do we do if x plus 3 is equal to 0? Because we can't cancel them, and those expressions wouldn't be the same. However, if x plus 3 is 0, then the numerator is also 0, and the input for a logarithm can't be 0. The logarithm doesn't have 0 in its domain, which means that x can't be negative 3, and this is possible to do this cancellation, right? Because x plus 3 is not going to be 0. Okay, so in this case, since we know that x can't be negative 3, then we know that x squared minus 9 over x plus 3 is equal to x minus 3. So now we have 3 halves times the logarithm of x minus 3 plus the logarithm of x plus y. And we can't use the product property just yet because we have this coefficient up front. So we need to move that in here as a power. Let's go ahead and do that. We're going to have logarithm of x minus 3 to the 3 halves. And then plus logarithm of x plus y. And then finally, we can go ahead and use the product property. If we do that, we have the log of x minus 3 to the 3 halves times x plus y. And we're done. Okay, here's one final example before we move on. The first thing we're going to want to do is move these coefficients inside as powers of the inputs on these logarithms using the power property. So if we do that, we're going to get log of x squared plus 1 to the 1/3 power, and then minus log of x minus 3 to the 1/3 power. And then now we just have a quotient property to deal with because we have two logarithms of the same base being subtracted from each other. So we can write all this as log of x squared plus 1 to the 1/3 power divided by x minus 3 to the 1/3 power. And then a minute ago we said if we have something like a to the b over c to the b, for example, that's the same as a to the c, or sorry, a over c all to the b. Right, so when we have numerator and denominator with the same power, that's the same as if the whole fraction is raised to that power. And since in this case we have numerator and denominator each raised to the power 1/3, we can put these all in the same bracket and then raise to the 1/3 power. So here we have the logarithm of x squared plus 1 divided by x minus 3, all raised to the 1/3 power. And if you like the radicals better, then we can write this as the third root of x plus 1 over x minus 3. Okay, here's a slightly different application. Let's say that for some base b, we know that log base b of 2 is equal to, or approximately equal to, remember that's what the curly looking equal sign means, approximates to 0.4307. Base 3 log of, base b log of 3 is approximately equal to 0.6826, and base b log of 7 approximates to 0.1 approximates to 1.2091. There it is. How can we actually find what the log of 6, the log of 2/3, and the log of 28 are? So we can do this by using our properties to split these inputs up. So if we do that, we're going to get log base b of 6. 6 can be written as 3 times 2. And then we can use our property. That's the log base b of 3, which we have right here. And then plus the log base b of 2, which we have here. So this is going to be 0.6826 plus 0.4307. And if you use a calculator, you're going to get that this is just about 1.1133. And I really should be using these curly equal signs to show that we're approximating these logarithms. Okay, same idea here. We can split this up as log base b of 2 minus the log base b of 3. So that's going to be 0.4307 minus 0.6826. Then once again using a calculator, this is minus 0.2519. Okay. So this one's a little bit harder to see. 6, it's easy to see that that's 3 times 2. How can we break down 28? Well, we can tell that 28 is even, so we can pull out a 2. And then 28 divided by 2 is 14. And then 14 is also even, so we can pull out a 2 again. 14 divided by 2 is 7. And 7 is prime, so that's as far as we can go. 2 times 2 times 7. We've shown that 28 is 2 times 2 times 7. And that's how we can break apart that 28 right there. So this is going to be the base b log of 2 times 2 times 7. We could do these one at a time, I suppose. We could do this as 2 times 2 and then times 7, so log base b of 2 times 2 plus log base b of 7. That's equal to log base b of 2 plus log base b of 2 plus log base b of 7. But really what we've shown is that even if we have more than two things multiplied together, like in this case we have 3, then we can always split those up over a sum. Okay, and then I don't have time or space to write out all 3 of these, but it's going to be 0.4307 plus 0.4307 plus 1.2091, and if you use a calculator on this, you're going to get 2.0705. So here I didn't use the calculator to evaluate each of these logarithms. I just knew what each of the original logarithms were for 2, 3, and 7, and using the rules I was able to find out what each of these logarithms was. And now, the moment you've all been waiting for, the change of base formula. So what this says is that the log, the base b, so the base b log of x, is equal to the base a log of x divided by the base a log of b, the base of the original thing that you started with. So it's kind of hard to see why this might actually be useful. But imagine that a is a base that you really like to deal with. So for example, a equals 10, something like that. And then b is a base that you really don't want to deal with, like 7 or 132, or literally anything else but 10 and e, for which you have handy buttons on your calculator. Then you're able to convert your logarithm just into the base that you like. So for example, say we have the log base 5 of 29. You might notice that 5 is neither 10 nor e, so let's convert this into a logarithm that we do like. So let's use the base 10 log. So that means we let a equal 10 over here, x is 29, b is 5. Now what we have is the base 10 log of 29, which we can approximate with a calculator, over the base 10 log of 5, which we can also estimate with a calculator. So we can get some number for this. On the other hand, you may want to use the natural log, which is also fine. Natural log of 29 over natural log of 5. So we've turned something that we really don't know how to calculate into something that we do know how to calculate. So here is one final example that uses the change of base formula. Base 3 log of 47. Change of base formula tells us that's base 10 log of 47 over base 10 log of 3. And if you use a calculator, you should get something like 3.5046. 3.5046. So as you can see, the change of base formula makes your life easier in every conceivable way. And that's it for today.